Okay, good evening. So this is seventh lecture, and in the previous lecture we have discussed about the conservation of momentum equation for multi-phase flow problems. Okay, so today we will slightly discuss one concept related to that, and then we will quickly move on to the next topic, that is energy equation for multi-phase flows. And if time permits, then we will also talk about interaction of multi-phase flows with turbulence. Okay. So, this is what we discussed yesterday. This is all about the dispersed phase momentum equation. So, in terms of dispersed phase means we are talking about actually in terms of the volume of individual dispersed phase particles. Okay. So, there we concluded that if Fk is the force which is interaction force which is acting on an individual particle because of the continuous phase, and if in our total control volume nd number of particles are present, then whatever the earlier type of momentum equation which we have written considering the two fluid formulation, there whatever the interaction force we are getting, that interaction force is nothing but number of particles times the interaction force for a single particle. Okay. Now, one simple thing we will be experiencing, that if you have some flow, okay, and in that flow if you simply insert a fluid particle, so what will be happening? Of course, initially at the instant where you have just dropped the fluid particle into the flow, at that point of time fluid particle will be having zero velocity in the direction of the flow. So what I am trying to say this is the flow direction, and in this flow direction I have simply gently placed a flow particle, dispersed phase particle. So once I place this dispersed phase particle over here, of course in the direction of the flow at time t equal to 0, where t equal to 0 just represent the time when I gently placed the particle in the flow grid. So at this particular point particle will be having zero velocity. Okay. So it means that if UDI designates the direction velocity of the dispersed phase in ith direction, then this will not be equal to UCI initially. Okay. And of course, because of the flow in the rightward direction, particle will experience certain amount of interaction force, and because of this particle will also start accelerating. Okay. But what is the maximum limit up to which this particle will accelerate? So it will maximum try to reach the velocity of the continuous phase. So basically if you see, whenever a particle is present in a steady flow of continuous phase, you will be finding initially there is some relative velocity, and this relative velocity is nothing but the difference of particle velocity and the continuous phase velocity. But ultimately the aim of the particle is, the aim of everything in the nature is to come in an equilibrium with its surroundings. Okay. So in order to come in equilibrium with its surroundings, this particle will try to reach the velocity of the accelerating phase, continuous phase, so that there should not be any relative velocity between the two phases. Okay. So what we wanted to estimate, we want to estimate that in any given situation, of course in every situation there will be different dominant forces which are acting on the particle, but on an average basis, the time taken by the particle to reach to its equilibrium position is something which we call as nothing but the relaxation time. Okay, and relaxation, formulation of relaxation time will be completely different for different type of flow situations. Okay, so one simple situation, if we consider that, if we assume that only drag force is the dominant interaction force, so this is nothing but my dominant interaction force. So particularly if I talk about flow of solid particles, dispersed solid particles or liquid droplets in air, so there we will be finding that majority of the times my dominant force which is acting on the particles is nothing but drag force. Okay. So if I have to find out the particle relaxation time in this scenario, so what will be happening? Of course, when the particle is actually changing its velocity from zero velocity condition to the condition where it is trying to minimize the relative velocity with its continuous phase. Okay. In this duration, particle will be having certain inertia, and that inertia and drag force will be counteracting with each other, and these will, when both of these forces are actually balancing with each other, then we will be finding one equilibrium state will be existing for the particle velocity. Is this one clear? Okay, so if your drag force and inertia force, you can understand in a very simple sense. If you drop a particle, okay, likewise we say in case of raindrops also. So raindrops are coming from huge distance. So if we typically see, under the effect of gravity, if I simply do V equal to under root 2 GH, we do very basic physics problem in standard 11th and 12th. Okay, so what we do there? We say that velocity of the particle will be like this, but this will be only possible if we neglect the effect of air drag. Okay, but if we consider the air drag, then what air drag is trying to do? Air drag is trying to reach a situation where there should be smallest possible relative velocity between the air phase and the droplet phase. Okay, and so it means that whenever your drop has just started falling, its velocity is increasing. Okay, because gravity force is dominating over the viscous drag or buoyancy force. Okay, but what will be happening? As the drop is accelerating, along with the acceleration of the drop, magnitude of drag force is also actually increasing. So it is trying to reach a situation where this downward dominant force and the magnitude of drag force are actually balancing each other, and the condition at which these are balancing each other, corresponding to that, we will be getting the minimum relative velocity difference between the dispersed phase and the continuous phase. Okay, and the time taken to reach that condition is something which we are calling as the relaxation time. Okay, so in a typical situation, if I have, say, solid particles or liquid particles dominant in the continuous air phase, then we will be finding that drag force will be the one dominant force, and second will be inertia force. Okay, so if I simply balance the inertia, so if I consider my particle to be spherical, radius of particle is r, okay, and if I consider that radius of particle is r, and if I balance and mass of particle is, say, mp. Now if I balance the inertia force of the particle, so if I balance inertia of the particle with the drag force, then I will be getting one time scale, and this particular time scale is actually written over here, T mu, which is equal to mp divided by 6 pi r into mu c, where mu c is nothing but viscosity of the continuous phase. So this is my particle relaxation time for this situation. Of course, when your situation will change and the dominant forces are different, then value of particle relaxation time will also be different. All are clear with this idea? So what I have balanced, I have simply balanced the inertia force and the drag force. So if I balance inertia force and drag force, I will be getting one time unit, which is mp divided by 6 pi r mu c. So for a spherical particle, you know from your basic fluid mechanics, if you have a completely spherical particle and flow is happening around a spherical ball, then the total drag force, which is sum of the form drag plus viscous drag, skin friction drag, that is nothing but equal to 6 pi mu rv, the solution for the Stokes flow condition. Okay, is this one clear? So by using that formulation of drag force and inertia of the particle, which is nothing but mass into acceleration. So m into d square r by dt square. So I have not calculated exact, but we have just done the order of magnitude balance between the two components. Okay. So then we will be getting this as our relaxation time. Is this one clear? Okay. Likewise, there will be one more relaxation time if we also include the heat transfer into this. Once we invoke heat transfer, then there will be some relaxation time taken by a particle to reach the thermal equilibrium, temperature equilibrium with the surrounding phase. Okay, so that we will discuss after studying the energy equation. So this is nothing but relaxation time in terms of the hydrodynamic parameters. Is this one clear? Now, let's talk about our next equation, and this is nothing but our equation of conservation of energy. And equation of conservation of energy is nothing but our first law of thermodynamics, which simply tells us that for a closed system, net interaction of heat and work is equal to change in energy of the system. And for an open system, along with the heat and work interactions, we will be having yes, energy associated with the mass interaction. Okay, and whenever we will be talking about the flow of fluid, in case of fluid flow, which system we have to consider, open or closed? Open system, because whenever fluid is flowing, so whatever control volume we will be considering, across the boundaries of the control volume there can be mass interaction. Okay, so typically if you see, we have two types of quantities. One is called as extensive properties, second is called as intensive properties, and all the properties on per unit mass basis are called as specific properties, and all the specific properties are of intensive nature. Okay, so this is over here nothing but total specific energy. Okay, and this total specific energy E star is nothing but E. What is E? E is specific internal energy. So typically we don't every time use specific term, but if these quantities are represented by small letters, then we simply call this as specific energy. Okay, then I have half ui into ui, which is v square by 2. So this is nothing but my kinetic energy. Then I have gz, which is nothing but potential energy. Okay, so these are the specific forms of the energies. Now, when I will be writing the equation, I will be having first rate of change of energy within the control volume. So that is del by del T. Rho is my density and E star is, what is rho? And E star is total specific energy within the control volume. Okay. Then del by del xi rho E star ui. What is this? This is, yes, convective term to account for the energy interaction carried by the moving streams. Okay, so if you consider this is your control volume, and in this control volume, if I say I have, this is my boundary of the control volume. So first term is representing the changes within the boundary of the control volume, number one term. But you have some amount of mass which is entering through this, some amount of mass which is going out through this. So it means there are some energy interactions across the boundaries also. So this second term account for these energy interactions across the boundaries. So this is nothing but rho times U is your mass flux. Okay, and E star is specific energy carried by that particular mass. Okay, and what is this? Why I am writing here also E star, here also E star? Can you tell me? Because whenever I am writing this term del by del xi rho ui, this is representing the net mass outflux, net mass going out of the system. So whatever mass is going out of the system, that will go with the energy state equal to that of the system. So that's why I am writing over here E star. Is this one clear? Because we are talking about net mass outflux.
Energy outflux.
Yes. Rho U star is representing net mass outflux, and whatever will be going out, that will be carrying the energy of the system, E star. Okay. Then this is the total change in energy of the system. So total change in energy of the control volume has to be equal to net heat and work interaction. So Q, any heat interaction, W, any work done on the system. Okay. And then along with this, what is this?
Viscous effect.
Flow work. Okay. So whenever you have a moving term, then we are having some quantity which is called as flow work. So typically in thermodynamics, we call product of pressure into specific volume as flow work. Okay. And along with the flow work, there is one more term in the energy equation which is called as viscous dissipation term. Okay. So one is, if your stream is moving, then that stream is actually pushed by some pressure at certain point of time, okay, at certain location. So how much amount of energy we are investing to make that flow happen, that we are calling, that we account with the help of pressure into specific volume into mass flow rate. Okay, but along with that, whenever this flowing stream is moving, then some amount of viscous stresses are also created. Okay, and our flow is also happening against these viscous stresses. Okay, or even within the boundary also we can have some viscous stresses. So what these viscous stresses are doing? They are actually consuming certain amount of energy, which is called as rate of viscous dissipation. So when I am using this term sigma ij, so at the moment its meaning is minus P into delta ij plus sigma continuous sigma C, let me use sigma dash or sigma deviotric. This is for deviotric. So that's why I am writing dE into Cij. Is this point clear? So out of this sigma ij, whatever is the contribution of pressure into velocity, that will be coming in the form of flow work. And what is the contribution of sigma Cij into dE multiplied by ui, that will be coming in terms of the viscous dissipation. All are clear with this idea? Fine. Now, one interesting thing. So, I can also write that my del by del xi of rho into ui, this E star, whenever I will be substituting this term sigma ij as minus P delta ij plus sigma C dE ij, then one term I will be getting over here as, in this particular right hand side, what I will be getting? I will be getting one term after the substitution of sigma as minus del ui into P divided by del x I. This will become del xi only after we do substitution of P into delta ij. Because why this xj will become I only? Because this delta ij will be equal to 1 only when I equal to j. So I can replace this j with I. All are clear with this idea? Okay. So once I have replaced this, then this term and this term, sorry, this second term, both are having del by del xi. So what I have done, that del by del xi I have taken common, and from both these terms, sorry, I have also taken ui as common. So if I take ui common, inside I will be getting rho E star plus P. Okay, and then rho also I have taken common, which made E star plus P by rho. All are clear with this? So what I have done, on the right hand side, this capital sigma ij I have replaced with this term, and then here only I have at the moment considered the pressure term, and second term I am actually at the moment I have not considered. Okay, so once I take this pressure term to the left hand side and combine with the second term on the left hand side, then I will be getting this quantity as E star plus P by rho. What is E star plus P by rho? Enthalpy. So E plus P into specific volume, and specific volume is nothing but 1 by density. So this is equal to what our enthalpy, H. So that is what is done over here. So because we are writing E star for internal energy, so that's why this I am writing H star. E star for total energy actually. So that's why I will be calling this also as total enthalpy. So this I will be calling total enthalpy, which is considering kinetic energy and potential energy also along with it. Okay, all are clear with this idea? Now, this up to this point, whenever I am talking about, I am considering the common density and common energy content for the entire equation. Okay, it means till now I have not introduced any concept of multiphase flow. So up to this point, whatever I discussed, that is applicable for only single phase flow. Okay. No, time term is there. No. Below this, what we have done, just for the coupling of second and this term I have shown you. Okay. Rather than that, I have not considered the heat and work interactions. But yes, you can say that if second equation you want to give some name, then you can call it as steady flow with no heat and work interactions, and what else? And neglected viscous dissipation. So then you can call, yes. So this is the physical meaning of this entire equation. Why steady? Because del by del T term is 0. No heat and work interaction because Q and W I have not considered. And from the last term only I have included the pressure part. But dissipation part I have actually neglected. So that's why if you want to name this equation also, so you can call this for steady flow with no heat and work interactions and negligible viscous dissipation. Okay, all are clear with this idea? Now what we need to do, we need to extend this idea of the energy equation for our multiphase flow problems. Okay, so how to extend this for multiphase flow problem? So now whenever I will be defining the energy, I am using subscript n. What is the meaning of n? It means I am referring to a particular phase. So it means this is total specific energy of a particular phase. That's why whenever I am using kinetic energy, here also I am using a particular phase. Okay. Then, what are these two terms? These two terms are identical to first two terms in the left hand side, but now within the control volume, total control volume is not filled with the same fluid. So that's why I am multiplying with alpha n, volume fraction. Okay, and at the same point of time, density also I have to consider for that particular phase. Okay, all are clear with this idea? So it means this is the total rate of change of energy of nth phase within the control volume. Is this one clear? Now comes important task, that is to account for the heat and work interactions. Heat and work interactions can be multiple. Plenty of heat and work interactions I can have. In a multi-phase flow situations, these will be one additional than for a single phase flow situation. For a single phase flow situations, I will be only having two types of interactions. Something coming from outside, like work interaction with the surroundings. Okay, so for a single phase flow, surrounding will be everything outside the control volume. But whenever I will be talking about a particular phase, then surroundings are two. One surrounding is outside the control volume for that particular phase, and another its immediate surrounding is all other phases present around it. Okay, so it means that if all other phases present around it, they are applying certain amount of pressure or forces on that, so these will also apply certain amount of work interaction with that particular phase. Is this point clear? So that's why whenever I am talking about the work interaction, I have splitted this into two parts. First is WAC. What is the meaning of WAC? All the work interactions which are coming because of the continuous phase, means from its immediate surroundings. So that is any work supplied by continuous phase plus what continuous phase is doing. Continuous phase is applying certain amount of stresses on the dispersed phase. Okay, so that's why velocity of continuous phase times sigma c ij. Is this point clear?
Zero viscous dissipation.
And then next is not viscous dissipation. What is WAD? Work done on the dispersed phase from external surroundings. Okay, what is the meaning of external surroundings? Say you have a steam turbine. Steam turbine is rotating. Okay, so in case of steam turbine, if you see, along with the steam, some liquid particles have also formed. And if you are considering that these liquid particles are actually acting as dispersed phase in the steam. So these liquid particles, whenever they are striking with the blades of turbine, they will also exchange some work. So that exchange of work with external surrounding is WAD. And this WAC is when these steam particles are interacting with the yes. Okay. Similarly, so if you do like this, then what you will be finding? Are you understanding this point or not? Or do I explain it again? Repeat. Okay. So what I am saying is, for example, if you have a steam turbine, so it will be having multiple turbine blades like this. Stage wise, these turbine blades are increasing in size. And this is my control volume. And in this control volume, see, this is my outlet of the steam. So if I say in this control volume I am having mainly as steam. So what is steam? Steam is nothing but my continuous phase. Okay. And along with this, if I say some small droplets of liquid are also present. What are these liquid droplets? These are dispersed phase. Okay. So if you see, this dispersed phase can interact with the surroundings. Okay. So if this dispersed phase is actually sticking on the turbine blades and then moving with the turbine blades, so it means it will be exchanging certain amount of work. Okay, so that work I am writing it as work done on dispersed phase from external surroundings. Along with this, what will happen? This continuous phase, which is steam, that is also interacting with these blades. So when this continuous phase is interacting with blades, that work I am writing as WC. But in addition to that, continuous phase from surroundings can also have viscous stresses other than the rotation. So that is something which I have accounted over here in this second term. All are clear with this idea? So now, with this knowledge, if I try to extend now the complete individual phase energy equation, so how it will be looking like? So what I am writing now is nothing but individual phase energy equation. So what is this? Individual phase rate of change of total rate of change of energy within the control volume. This will be equal to Qn, heat interaction with surroundings. With, I am using word external surroundings. External surroundings means, of course, because for any phase, whatever is outside that phase, that is its surrounding. But what I am saying is external surrounding means any surrounding which is outside the whole control volume. Okay. So dispersed phase, how much it is actually interacting heat with. So if I consider, say, this particular droplet to be my nth phase, so right now I am referring to heat interaction of this with outside the boundary of control volume, this Q1. All are clear with this idea? Then similarly, this particular droplet's work interaction with external surrounding, that I am calling as Wn. Okay. Then I am referring one more term, Qin. What is the meaning of Qin now? Now this drop can have heat interaction with surrounding steam. So what is that heat interaction is, that I am calling as Qin. So this is with other phases. This is with other phases within control volume. All are clear with this idea? You have to segregate this very, very precisely, okay? Because you have a mixture present. So in that mixture, some interactions are with external surroundings, some interactions are with other surrounding phases within the control volume. Okay. So all the terms which are with Q and W, and these are with external surroundings for nth phase, and Qin and Win are the heat and work interactions with other phases within the control volume. Okay, so it means this Qin and this Win is happening within the control volume. Is this one clear? Now what I was previously telling, that a continuous phase will apply certain amount of pressure and stresses on the dispersed phase, and because of that there will be some work done. So that work done is actually accounted in this Wi. All are clear with this idea? Then other than this, what we will be having? Other than this, as per our discussion of momentum equation, we have a control volume which is at its boundary everywhere in control with the in contact with the continuous phase. Okay, so that continuous phase will be having some shearing action. So because of that stress, shearing action or normal action, some work done will be happening at the boundary of the control volume. So this is the last term. Work done at boundary. And boundary is always in contact with which phase? With continuous phase. So that's why I have used over here Kronecker delta operator, delta n, and this will be on when delta n is equal to C, then only it will be 1, otherwise for all other phases it will be equal to 0. Because all the other dispersed phases, these are not interacting with the boundary. So as these are not interacting with the boundary, these will not experience any work interaction at the boundary. All are clear with this idea? Anyone is having any doubt? Please discuss, because this is important.
सर ये जो ऊपर वाली इक्वेशन है WAC
Yes.
ये कंटीन्यूअस फेज के
This is only for continuous phase. Yes. Okay. Now, can you tell what I have written next?
नेट एनर्जी चाहिए इन सिस्टम
So, say you all are 20 people sitting here. I am giving X amount to him. You are giving Y amount to him. He is giving Z amount to him. So what is happening? Whenever, now he was the point of consideration, he was my nth phase, and on him I have seen XYZ interaction is positive. Okay. When I will be the point of interaction, then on me, because I had given X to him, so on me that X will be with negative sign. When I will be considering him, Sushil, as the nth phase, then minus Z will be interaction to him. So it means between Sushil and Kesav, whatever interaction was there, that is balanced. Between me and Kesav, whatever was there, that is balanced. If I do summation for all the phases. So that's why within a system, whatever the internal heat interaction will be there, whenever I will be doing the summation for all the phases, that comes out to be 0. Because total energy is a conserved quantity. You cannot destroy energy. Okay. So in the similar sense, any work interaction within the system. So the way I told XYZ for heat, same sense I can exchange XYZ in terms of work also. I can push him. So that is work interaction on positive on him, negative on me. Okay. Is this one clear? So this way, when you will be doing summation for all the phases, then summation Qin will be 0, summation Win will be 0. In a similar way, if there is epsilon n means any other type of energy interaction between the phases, that also ultimately will be equal to 0. Is this point clear? But can this Qn and Wn be 0? No, because these are coming from outside. Okay. And whenever I will be doing summation, then summation I am doing within the control volume only. I am not doing summation, I am not considering outside the control volume in the summation sign. Is this point clear? What is the meaning of summation Qin? The meaning of summation Qin is if in my control volume there are 1, 2, 3, 4, any 5 phases are present. Whenever I will be doing summation Q, it means I am doing summation Qi5. Anything outside 6, 7, 8 is present, I am not at all bothered about that. Okay, so that's why only summation Qin will be 0. But what is this Qn? Qn is interaction from external surroundings. So when I am doing summation Qn, it means I am not doing summation, I will be doing summation only for 1 to 5. I am not doing summation with 6, 7, 8. So that's why that term cannot be equal to 0. Is this one clear? Why? How? This Qn and Wn are there? These are not. Of course, how internal energy will increase? If you are able to increase internal energy, it means you are able to generate energy, create energy. You cannot create energy. No, we don't create energy. Every time we exchange energy and convert it from one form to another form. For example,
सर इस इक्वेशन में जो ऊपर वाली इक्वेशन है, अगर ये सिर्फ अलग एक फेज के लिए अगर हम डिनोट करें तब उसका इंटरेक्शन आएगा.
Yes, when we will be applying for a single phase, then interaction will come. But if we do summation, then this internal interaction term will become 0. Now your question is, like, these interaction terms should not be 0, huh? That is what you are saying. Of course, उसका effect आ रहा है. Whenever we are talking about an individual phase, on an individual phase, it is causing increase or decrease. But whenever as a whole I will be talking about the control volume, then all internal interactions has to be 0. So that is affecting individual phases, but not the entire system. If you have to affect the entire system, then there should be some interactions with the surroundings. You pack this room, okay? You start walking here, considering that you are a molecule, okay? So if all of us are molecule, and if I try to push some molecule in specific direction, then there will be exchange of energy only within the system. But if you see outside, if you segregate everything from outside, and if you don't consider any interaction with outside, like if you make an isolated system, this room, then total energy state of all of us will not change. That will always be same. At some point of time, it can be different. For example, I am walking, so my energy in the total system can be in the form of kinetic energy. All of you are sitting, your energy may be in the form of some potential energy at your respective locations. But overall energy of the system will be always conserved if you are not considering any interaction from the surrounding. Okay? So now, then I am doing another thing. So I am considering only two phases. If I consider only two phases, one is dispersed phase and second is continuous phase. In that case, what will be happening? QIC has to be minus QID. Simple thing. Okay, so whatever, if only two phases are present, say all of you are continuous phase, I am a dispersed phase. So whatever energy I am giving to you, so it is loss on me and gain on you of the same magnitude. So that's why one is positive, one is negative. So this is very simple. Means any force on dispersed phase multiplied with its velocity, that will be nothing but work done because of the continuous phase on dispersed phase. Is this one clear? So now, when I will be doing summation of all external energy interactions, then what I will be getting? Total heat interaction with external surroundings. Okay. Similarly, total work interaction with external surroundings. So when I am writing individual Q1, Q2, Q3, W1, W2, W3, it means that, say I am 1. So Q1 amount of heat I have gained from external thing. He has got Q2 amount of heat. He has got Q3 amount of heat from the outside. So whenever I will be doing summation of all the outside heats, that will be Q1 plus Q2 plus Q3 likewise. So it means total heat this room has got from the outside surroundings. Is this one clear? Similarly, total work this room has got from the outside surroundings. Okay. So now what we have done is, we have done the summation of the previous equation. All individual phase equations. So if I do summation of all individual phase equations, then what I will be getting? Combined phase energy equation. This is my combined phase energy equation. So if you see, this first term is as it is sum, second term is as it is sum. Only thing is, I have included this term also in the left hand side. And here you can see one thing. What is in this term? UCJ sigma Cij. Why C? Because only continuous phase is in contact with the boundary. Because if you see your individual phase momentum equation, individual phase energy equation, in the individual phase energy equation, this term will be 1 only for a continuous phase. For all other phases within the control volume, this entire term will be equal to 0. So that's why this term is only appearing once. As it is appearing once, I have taken this to left hand side and added with this term. Okay. So that's why you can see here there is summation sign, but with this term there is no summation sign. Clear? And whatever the internal terms were there, internal terms have become 0. And only terms now we have is because of the external heat and work interactions. So this is nothing but our combined phase energy equation. All are clear with this idea? Now, what we can do? If I know this thermodynamic transformation in between internal energy and the specific heat at constant volume, then it is nothing but Cv n times Tn plus constant. If I do this substitution, I can replace this equation in the form of temperature. And this is now individual phase energy equation in temperature form. I am not going to derive or explain it further. It should be very clear now. So only thing what we have done is internal energy of each phase we have replaced with the Cv calorific value or specific heat? Specific heat at constant volume. Okay, multiplied by temperature. So if I do so, then I will be getting this equation. Now in this equation, because I am talking about all the individual phases, that's why it is called as individual phase equation. Okay. Then next, if I do summation of the previous equations which are in the form of temperature, then I will be getting combined phase energy equation in temperature form. Okay. Whenever it is written in temperature form, these terms are further reduced. So let me not explain at the moment. We will discuss about these terms later on when we will be dealing with the specific cases. Okay, because in generality this may look very unobvious to you. Okay, so when we will be talking about the specific cases, then we will discuss about this. Fine. Then we have, what is this? Now you should be able to tell. Area averaged individual phase energy equation. Fine. Now I need not to explain it again. Okay. What is this? Area averaged okay. Area averaged combined phase energy equation. Now, the way we were having temperature, the way we were having this hydrodynamic relaxation time, in a similar sense, we will be having some temperature relaxation time. What is the meaning of temperature relaxation? So, of course, in a system, if heat transfer is happening between the multiple phases, it may happen that my temperature is different, your temperature is different. So, what will be happening? We will be having heat transfer in terms of conduction, convection, or radiation. Okay. So, this heat transfer will keep on happening till the time thermal equilibrium is not established between us. Okay. So, thermal equilibrium is a state at which there is heat transfer It means I am transferring some energy to you, you are transferring some energy to me, but we are transferring in such a sense so that the net energy transfer is equal to 0. So it means even if there is energy interaction, our temperatures are fixed, not changing. Okay. So what is the time required once we put two different phases, then in what amount of time actually these will be coming to that situation. Okay. So first part is, we will, of course, again this is a complicated problem, because first thing is, if you have a dispersed phase, heat transfer has to penetrate through the surface area. So you should know the distribution of surface area present in the system, and then only you can actually determine the further energy interactions, heat interactions. But for the simplicity, we will consider that we have spherical particles. What we have is spherical particles, and these spherical particles, say, are moving in a gaseous medium, and these spherical particles can be of solid or can be of liquid. Okay, so out of these solid and liquid particles, if you see, surrounding phase is gas, and inside either I have solid or I have liquid. Which one will be having highest thermal conductivity? Of course, solid or liquid. So it means out of this, gas will always be having the lowest thermal conductivity. If gas is my continuous phase, then Kc is smallest. Okay. If I consider that my dominant mode of heat transfer is conduction only. Okay. So it means that whatever heat this particle is transferring to outside, that is transferring through the mode of conduction only. Okay. So which thermal conductivity will be dominating over here? Thermal conductivity of the liquid or solid, or the continuous phase gas? Continuous phase. Okay, because from inside heat may come at the faster rate, but outside it will be traveling only at the pace of conductivity of the gas. Okay, so that's why if I have to determine conduction heat interaction between particle and the continuous phase, so how I can write it? 2 pi r Kc into Tc minus T. Okay, so Tc is temperature of the continuous phase, Td is temperature of the dispersed phase. Now one more assumption I am invoking over here, that entire dispersed phase is at uniform temperature. So it means thermal conductivity of the dispersed phase is so high in comparison to the gaseous phase. Of course, in terms of solids and liquid, if these are present in gases, we can easily put this assumption. So their conductivity will be so high that their temperature will be kind of uniform. Okay, so this is the conduction heat transfer, only conduction. Now if I invoke convection, then what will be happening? In terms of convection, there should be some relative motion between the particle and the gas, okay, surrounding gaseous phase. So how to account for that? To account for that, of course, convection is again a semester long course and a very complex course. For different situations, rate of heat transfer in convection mode will be different, but easiest way to determine convection heat transfer is to determine the Nusselt number. Because what Nusselt number does, Nusselt number represents nothing but convection heat transfer upon conduction heat transfer is easy to determine, already we have determined here, and if I know Nusselt number for certain situation, then I can predict the value of convection heat transfer. Okay, how I can know this? There are different correlations or theoretical solutions available for various simplified situations, and of course if I have to know the Nusselt number, I must know the effect of relative motion and heat storage capacity of the material. These two things will be actually governing our heat transfer coefficient. There are many parameters, but when we non-dimensionalize, then ultimately my Reynolds number and Prandtl number controls the value of Nusselt number for different situations. Okay. So what I will do over here, for this situation which we have taken over here, like Nusselt, spherical particles are present in a gaseous medium, Nusselt number can be approximated as 2 plus 0.6 times Reynolds number power 1 by 2, Prandtl number power 1 by 3. Here Reynolds number is equal to 2WR by nu C. What is nu? Kinematic viscosity, which is dynamic viscosity of the continuous phase divided by its density. And what is W? W is relative velocity, which is nothing but velocity of dispersed phase minus velocity of continuous phase. So Reynolds number is calculated based on the relative velocity. Okay, and R is 2R is radius, 2R is diameter. Okay, so that is length scale to calculate the Reynolds number. And what is the definition of Prandtl number? Rho Vc into Cpc divided by Kc. Okay, so K by rho C represents Kc by rho C nu C. What it represents? Alpha C, thermal diffusivity. So ratio of momentum diffusivity, like kinematic viscosity, divided by, sorry, I should have written here Cpc. Ratio of K by rho C Cpc is nothing but thermal diffusivity, and nu C by alpha C is my Prandtl number. Okay. So now, if I know this Reynolds number and Prandtl number, then I can determine the Nusselt number. And if I multiply Nusselt number with conduction heat transfer rate, then I will be finding the combined conduction plus advection. It means convection heat transfer rate. Okay, but till the point we have neglected the radiation mode of heat transfer. So we are not considering at the moment radiation mode of heat transfer. Okay. So now with these parameters, if I have to define some relaxation time, so how I can define relaxation time? Say QID is the internal amount of heat interaction between the particle and the continuous phase. So that heat interaction I can write as 2 pi r Kc into Tc minus Td. This was the conduction. When I have multiplied this with Nusselt number, it has become convection. And then I have multiplied with Nd. Say in my total control volume, Nd number of particles are present. So this is nothing but my net heat interaction with the dispersed phase particle. And this must be equal to rate of change of temperature of the particle. So rate of change of temperature, so density of dispersed phase particle multiplied by alpha d and its specific heat, okay, into total time rate of change of the temperature of the dispersed phase. Is this point clear?
0.
Why?
Total difference between.
If you are sitting in this room, all of them are adding certain amount of heat to you. So what will happen to your temperature?
Overall temperature to 0
Am I talking about overall temperature here?
Summation to mark.
Here is summation.
ND.
See, these are number of particles. Okay, so say these are ND. And then here what I am having? Am I taking the sum of all dispersed plus continuous phase? I am simply talking about all the dispersed phase particles. Okay. Is this point clear? So this is dt d by dt. Okay. So now if we further simplify this equation, we will be finding that dt by dt is nothing but Nusselt number by 2 into Tc minus Td by Tt, where this Tt term is having dimensions of time, okay, and this, if you further calculate, it will be coming out to be Cs d rho d into r square by 3 kc, which is our actually temperature relaxation time. Is this one clear? So this was the original equation. This original equation we have actually tried to little bit algebraically adjust. So in this original equation, this denominator is actually having the dimensions of time, and this term is equal to this whole quantity. So that's why I am calling it as temperature relaxation time. Is this one clear? So it means that if you consider your all particles to be spherical and
Same radius.
of same radius, and then all the particles are having uniform temperature, then simply you can use this time to determine that what will be your temperature relaxation time. Like in how much time both the phases will reach the thermal equilibrium. Is this one clear?
And of same radius.
Yes. Because we have considered the identical heat transfer rate for all Nd number of particles. Is this one clear? So it means that, but one important point, this formulation of temperature relaxation time should be applicable only for spherical particles present in the gaseous medium. Okay? Because if I say that my solid particles are present in liquid medium, then liquid thermal conductivity and solid thermal conductivity will be comparable. So there will be significant existence of significant temperature gradients within the solid particle present. Okay. So here, why we are saying that gradient is not present within the particle, like particle is almost at uniform temperature, because surrounding phase is gas, which is transferring heat. Convection rate of heat transfer is low in comparison to the conduction heat transfer within the rate of conduction heat transfer within the particle. So because of that, this is nothing but a low Biot number flow. Okay. Is this part clear?
एनडी कहाँ गया? एनडी नंबर पार्टिकल्स इक्वेशन में जो है वो
So here if you see how you can replace alpha d, Nd into volume of, and then volume you can write all spherical particles 4 by 3 pi r cube. Okay, is this one clear? So here in this equation there was some Nd. When we have got this equation and final Tt term, here there is no Nd, and previously we were having alpha, now there is no alpha. So alpha d is volume fraction, that is nothing but number of particles times volume of each particle. All spherical particles volume is 4 by 3 pi r cube. So after that Nd and alpha are eliminated. Okay. Up to this point, is it clear? So we will stop with this. We have completed our discussion on energy equation. Now interaction with turbulence we will discuss in the next class. Okay. If you have any doubt, please discuss.